Hello Paimarats, welcome to the solution of exercise about selling lemonade, which is an economical one where we are going to look into a demand curve, quadratic functions, and I'm also going to show you how to interpolate functions in Python. Let's do it. Imagine you decide to mix lemonade and sell it on the street. Naturally, the question is how much should you charge for it in order to maximize your profit? In economics, so-called demand curve describes the relation between the price of a product and people's demand for it. First, we are going to consider the most simplest form of a demand curve, which looks like this. It is a linearly decreasing function. The meaning is that at price equal to 0, we are going to sell unity or 100% of lemonades. As we increase the price, moving right on the x-axis, people's demand for it is going to drop until we hit the price of 100, where nobody will buy any lemonade from us anymore. Producing lemonade is cheap, but it's not for free, so making a single lemonade will cost us 10 money. On the top of that, we need to make an initial investment to buy a juicer for 1000 money. First question is, how do you optimally set your price in order to maximize your profit, let's say from 100 lemonades? In the second part of the exercise, we are going to consider a real-life example of a demand curve from the experiments on people. And the question is, are we going to earn more or less money if we apply it to our lemonades? Let's get to it. We have already imported standard modules, numerical Python, and matplotlib pyplot for plotting graphs. Then we have some global settings for all the plots in our notebook. We run the cell and we are ready to tackle our problem. So what do we want? We want to maximize profits. So profit is a function and it depends on the price we set for our lemonade. So first task is to define the values for the independent variable, which is the price of lemonade. We are going to linearly space it, linspace method, and prices are positive, so we start from 0. We had maximum price 100, and let's make 101 values in between. Now we need to translate the demand curve from the demand plot above into a linear curve equation in the form of demand equals constant A times x-axis price plus constant term B. That means finding A and B, because we already know or define the price. Since a line is defined by 2 points, the easiest way is to substitute values of intercepts with x or y axes, which means when price is equal to 0 or demand is equal to 0. So first, let's make price equal to 0. So that means the first term is equal to 0. At that price 0, demand was 1. So necessarily B needs to be equal to 1. Now, if demand is 0 and B is 1, then the first term needs to be equal to minus 1. Demand was 0 for price 100. So something times 100 equals to minus 1. That means A equals to minus 1 over 100. Note that our demand curve is in the form of a fraction, and therefore you can think of it as a demand for a single lemonade. But in reality, we need a demand for n lemonades. In real life, you can also imagine that producing more and more will eventually saturate the market. That means that demand for your 1 billionth lemonade will be probably lower than for the first one. However, we will assume that we are small producers and we have potentially 8 billion customers, so simply our demand for n lemonades will be n times demand for 1. So in total, our demand for 100 lemonades is going to be 100 times, and we have already translated demand for 1 lemonade into a linear equation, where we had 8 times price plus constant term B. So that is our demand. Now we are ready to calculate our income. Income depends on the price we are going to set for the lemonades and fraction of lemonades we are going to sell, which is given by demand. So price time demand is our income. And what are our expenses? So those are defined in the task. Investment was 1000 for the juicer. Production is 10 for one lemonade, but we have 100. And total expense will be investment plus production cost. Production. Let's run the cell. And now the profit. The profit is what comes in, what comes out. So that's income minus total expense. Now let's plot our profit curve. So we are going to use PLT and function plot, which takes the x values, which was price, and we want to plot our profits. So profit, and we can also label it, let's say, profit. Run the cell. Surprise, surprise, our profit curve has a shape of quadratic function, and this shape makes sense. So if we set the price 0, we are going to get rid of all the lemonades, but we are going to be minus 1000 of the investment and minus production cost, which is 100 times 10, another 1000, in totality minus 2000. If we set the price 100, then we are not going to sell any lemonade, and minuses will be the same. However, we will still have 100 lemonades which we can drink. Maximum profit is somewhere in between. From the symmetry of the parabola itself, we can see that the maximum profit will occur exactly between 0 and 100, which is at price 50. However, how many lemonades are we going to sell at that price? So the leftover fraction is calculated as 1 minus demand. Our demand is our linear equation, and we are at price 50. So if we put the price equal to 50 and subtract from 1, we are going to get the fraction, which is 0.5. So we are going to achieve maximum gain when we sell only half of our produce. This might be a little surprising, but it all depends on the shape of our demand curve which we had in the task. So how do we find the solution in general? We can proceed in a similar way as in the pizza exercise. We have a function for our profit, and we use a Pythonic method analogous to fsolve. Just we don't want to find the roots of quadratic equation, but we want to find its extreme, either minimum or maximum. And for that, function minimize exists from scientific Python package module optimize. However, our function needs many inputs because our profit not only depends on the price, but we had also investments, production costs, and how many lemonades we are going to produce. Therefore, we are going to choose alternative, not so optimal, but quick and easy way. And that is simply looking for the maximum value of our profit array. This is possible to do even by eye when we print our profit array. So we have a values and we go by eye and find the maximum, which is somewhere in the middle, and it equals to 500. In Python, we have a design function for it, which is called max. So max will find maximum of the array and it prints maximum 500. However, we want to find at which price we gain the maximum profit. So that we want to find the argument of the maximum. So for that purpose, we have argmax function, again applied to profit. And we get 50, which looks correct, but be careful, because argmax returns a position, that means the index of our independent variable, at which the 500 will appear. And this index needs to be applied to our price array. So we need to write price, and now indexing goes with square brackets, and we input our 50. Return is again 50. We can also merge both operations together. So we had price, and now indexing, square brackets, and now the argument of the function. So np argmax, and there goes profit. And we get the result 50 right away. So NP argmax gives correct result only because we created the initial array as we did. So we created 101 points between 0 and 100. Therefore, at position 50, we have value of 50. I know this is confusing and it really needs some time to get used to what is index of an array and what is a value of an array. We can also compare what are the types of those two things. So first, I write type and our argmax. If we run the cell, it returns numpy integer. So numpy and integer makes sense because we cannot, for example, ask what is the value at position 8.7. So we cannot index with real numbers, we can index only with integers. However, if I write type and the price, so I am asking what is the type of the values in my array, then I get float, and float represents the real numbers. Now, warning number 2. Minimize is the better method because the solution is numerically exact. Yes, minimize is a correct method to find the maximum. The trick is that we will be minimizing function minus profit. Using our max was that we just search the values we created in the beginning. Therefore, precision of the max method will depend on the frequency or how many values we define in the beginning, which is so-called sampling. That's the end of the first part of the exercise. In the second part, we are going to apply a real-world demand curve to our lemonade and ask a question, are we going to earn more or less money with that? See you there!